This video presents an executive summary of the predictable bin picking of shafts and axles project by Pickett 3D, a provider of automation solutions, adding unparalleled flexibility and intelligence to challenging production scenarios. Leveraging the power of 3D vision and robotics, we help manufacturers worldwide to speed up time to market, gain control over operational costs, reduce the factory footprint, and add value to the human operator role on the work floor. Easy to use, all-in-one Picket 3D solutions include a robust and open technology platform. Our participation in the Trinity program contributes to improving the agility of European SMEs in the manufacturing industry. And the project, the predictable bin picking of shafts and axles, is relevant to industries where parts have to be moved from a bin to a conveyor or a production line. A robot cell that is required to do this task typically includes a robot, a gripping solution, and a detection method. In the presented project, the detection method is using the Picket Vision system, and the gripping solution is the Picket Billet Picker. The main efficiency indicator of the robot cell is cycle time, which represents the time when a new part needs to be added to a production line. To make the production line successfully work, the cell has to provide the part every few seconds in a continuous way. To achieve this goal, bin picking cells with the gripper and the camera solution from Picket was set up at different locations. The cells were running for 24 hours, and the time-lapse videos from these demos are available on the YouTube channels of the channel part of the partners, AI Cloud and Delta Tech. The results achieved from the local demonstrations allowed us to conclude that firstly, the Picket solution is capable of delivering the desired functionality of picking shafts, axles, and other cylindrical objects. Secondly, the billet picker provides solutions to existing demand in the market. The billet picker solution has been already sold to two first local customers during the project. This use case is presented by Trinity SME, small and medium enterprise, Picket located in Leuven, Belgium. Other partners where the robotic demos were set up are AI Crowd, located in Žilina, Slovakia, and Delta Tech, located in Győr, Hungary. AI Crowd is an integrator that delivers solutions to manufacturing companies through technological transformation. They take care of the technical background of this transformation so that companies can easily and effectively fulfill their vision. They are experienced in the development and production of machines, and their creativity supplies comprehensive progression solutions for any type of production. AI Crowd has an extensive experience mainly in the automotive sector, but also in the footwear, food, and engineering sectors. Delta Tech is an integrator that specializes in designing and manufacturing special-purpose machines, assembly lines, and production lines based on individual requests since 1995 in Hungary. Their activities include mainly the automotive, plastic, metal processing, and electronic industry area. The quality of their delivered solution is based on mechanical and electrical engineers and computer programmers. They have 15 years of experience in design and manufacturing. Both companies, together with Picket, worked in harmony towards common goals to achieve successful results presented a few slides later. The purpose of Trinity predictable bin picking of shafts and axles is to provide a reliable solution to an existing demand to automate manufacturing processes. A lack of workers has a negative influence on productivity and economic indicators. Finding employees to do repetitive tasks has also become more challenging, especially in harsh working conditions, exposed to dirt, high temperature, and noise. That's where smart automation is key to success. and this automation doesn't have to come at high costs. Predictable predictable bin picking of shafts and axles project demonstrates to shaft and axle manufacturing companies that bin picking cells can today be implemented in a way that the performance is predictable, the installation time is limited, less than 1 week, and reconfiguration of the cell for different parts is easy, less than 1 day. Let's take a look at the results from the robot cells. Developing the solution and getting the performance metrics right for shafts and axle picking application is the key responsibility of Pickett in this project. Several tasks have been accomplished in order to achieve the previously mentioned goal. First of all, an adaptation of the gripper to cover an even greater range of the parts that need to be picked. Pickett created a large-sized gripper that covers a range of heavy billets from 15 to 60 kilograms and designed also a short-medium gripper for a specific customer application. Hence, the improvement of the gripper designs for better maintainability and modularity has been successfully completed. Secondly, an extension of the Pickett software has been developed with the following features. Focus regions. We extended the pipeline by including the use of weighting factors on local features of the parts to enhance detection. Environment modeling for collision prevention was also included, and an added pick point flexibility to allow more possible pick positions on the part with an easier setup. Next to that, an update of the Pickett robot interface has been done. We updated the Pickett robot communication protocol that allows sending extraction poses and directions to the robot. Moreover, robot example programs were updated for an easier setup of the robot cells. To validate the performance, integrators set up robot cells to the Pickett team support to demonstrate reliable billets and shaft picking. Billets picking was demonstrated by Delta Tech and shaft picking was presented by AI Craft. Open day events were organized at both premises to present the two robot cells. In this table, we see the main project KPIs that indicate the success of the demos. First, we have the cycle time, as explained later. It's the time it takes to pick a new part successfully. In the demo at Pickett, it was 12 seconds. In the demo at AI Cloud, it was 9.9 seconds. In the demo at Delta Tech with the cylindrical billets, it was 9.9 seconds. These three demos all achieved the target of less than 12 seconds. The pick success rate is the percentage of successful picks from the first trial. At Pickett, it was 94%. At AI Cloud, it was 97%. And at Delta Tech, it was 96%. And these all are higher than our goal initially stated for 92%. The required operator intervention was aimed to be less than a quarter hour or 0.15 of an hour. And this means that we want the cells to run smoothly for 24 hours with very minimal intervention in the cell. And this was achieved at Pickett, at AI Cloud, and at Delta Tech. Bin emptiness is also an important indicator because we want to try to empty the bins fully from parts. And the indicator was to empty the parts almost entirely and only leave less than 5 parts in the bin, and this was also achieved at all levels. Our demonstration contributes towards the Trinity goals to improve the agility of European manufacturing by delivering reliable automation solutions for bin picking scenarios across industries, forging, metallurgic, and automotive. The demonstration proves that it is possible to achieve predictable automation with a limited installation time and easy cell reconfiguration for different parts for various industries. Hence, this successful shaft picking demonstration contributes to ensuring Europe's welfare through intelligent, agile, and reconfigurable production. In this project, we proved that changing the picking tool design can be done in a timely manner. For example, adjusting the M gripper to a shorter dimension took approximately 8 weeks. Adaptation of the remaining tools can be done in a similar way, proving at the same time the high adaptability of the picking tool. There are several application scenarios where the billet picker solution can be applied. First of all, it can be applied in bin picking scenarios of different shafts and cylindrical objects in automotive, forging, and machinery industries. It can also be applied in other industries, such as bin picking of non-magnetic parts, using vacuum gripping modules instead of magnet modules. It can also be extended to the detection of pick and picking of box models like square billets. Thanks to Trinity's support, it was possible to cover the expenses necessary to build the local demonstration and to organize the dissemination activities. Next to that, Trinity supported the project in terms of advertising. In addition, all partners benefited from networking events. To conclude, the main objective of the predictable bin picking of shafts and axles demonstration is to show reliable bin picking of shafts, axles, and other cylindrical parts in real industrial scenarios, and to quantify performances to confirm the technical readiness of the solution for the industry. The seamless integration of a versatile gripper integrated with the Picket 3D Vision platform and specific software allows a robot manipulator to pick randomly placed objects in a bin to feed CNC machines. The Picket Vision platform and the modular tool help small and medium enterprises to automate repetitive bin picking tasks of different parts. To benefit from reliable automation, it is crucial to rely on compatibility. This compatibility is represented in the combination of software and hardware solution provided by Picket. More information about predictable bin picking of shafts and axles of this use case can be found on the website catalog. Please scan the QR code on the slide to reach this catalog. Don't hesitate to contact Picket 3D, AI Crowd, and Delta Tech to learn more about the presented solution. Scan QR codes below the name of the company to visit the website. You may also want to check the Trinity YouTube channel by scanning the QR code that is presented at the right bottom of this slide. Thank you for your attention.